So we were discussing the extraction of metals. और उसमें था कि I told you कि you've got these unreactive metals which are found in the native state. You've got copper as well, which is kind of unreactive, so that is also a lot of times found in its native state, but you can do electrolysis of aqueous solutions. I think we did this over here. कि आप ore लेते हो, उसको you dissolve it in acid, turn it into a solution. It's got copper 2+ ions. You connect it with a battery. The battery starts sending electrons. The negative cathode, it ends up providing electrons to copper 2+, and they turn back into copper metal, and you get this pink metallic deposit. Okay, so this was something that we did. And then there was reduction with hydrogen. What you could do is a more reactive metal always displaces a less reactive metal. That's another one. So more reactive metal displaces the less reactive metal, so in this case, what happened was that hydrogen is more reactive than copper. So hydrogen, if copper is forming compounds, you can react it with hydrogen, and hydrogen will steal all the oxygen. It will reduce it. Okay, loss of oxygen means, hydrogen is going to take away the oxygen and water is going to be formed. And that was reduction with hydrogen. And then what you did was that you have these other metals which are kind of slightly more reactive. Like iron is more reactive. Iron actively rusts. Like the reaction isn't very fast, but in terms of iron will always be found in the form of ores. Never in its original state, because iron will react with oxygen. So what you can do is you can react it with carbon. What carbon will do is it will take away the oxygens from iron, because it's more reactive. More reactive displaces a less reactive. So carbon dioxide would be formed, and iron will be produced in this way. The same happens to zinc as well. You can react carbon with zinc ores, and oxygen will be removed by carbon. Carbon dioxide will be formed, and zinc metal is going to be produced. And then you had these very reactive elements like aluminium. For aluminium, you can't reduce it with carbon, because if you have aluminium oxide, so for example, if there is aluminium in the form of a compound of aluminium oxide, carbon will not be able to do anything. There's not going to be any reaction. Why? Because carbon is less reactive. In the reactivity seas, carbon is lower down in the reactivity seas. It is less reactive, so probably no reaction is going to happen in that particular case. So carbon will not be able to take away oxygens from aluminium. So in that case, only electrolysis of molten electrolytes is done. So we were discussing aluminium in detail, and we had discussed iron, extraction of iron. Like in extraction of iron, we discussed that in detail. You have to remember that hematite is used as an ore, and there are impurities like sand, rocks, etc. Magnetite is an ore. What you need to do is you need to react it with carbon, so that carbon, being more reactive, would be able to pull. So carbon being more reactive, so this one is more reactive than iron. So you want the more reactive carbon to actually pull the oxygens away from iron. But the whole process was done in a blast furnace. What you did was you added hematite with carbon, which is in the form of coke, which is a coal, which is a type of coal that contains a lot of carbon. Hot air is blasted, and the coke catches fire. The coal starts burning up. The carbon in the coal starts reacting with oxygen and starts producing carbon dioxide, which is a very exothermic reaction, and a lot of heat is produced, and this heat melts all the mixture. And the carbon dioxide that is being produced, it further gets reduced by coke because there's so much carbon that it needs oxygen. So they're going to distribute oxygen among themselves, and carbon monoxide is going to be produced. The whole point was that you want the mixture to melt, because if it's at a higher temperature, particles are more energetic and they'll bump into each other a lot more, and you'll get a much faster reaction. So what you wanted was the carbon or the carbon monoxide to react with hematite, iron oxide. Carbon being more reactive, it's going to take away the oxygens and iron is going to be produced. The same happened with carbon monoxide. It turned into carbon dioxide and iron is produced. The purpose of limestone was that you wanted to remove impurities like sand. I mean, like if you take a rock, hematite, which is a rock, it's going to contain iron oxide, but it's going to contain a lot of other things as well, which are unwanted. So the sand is removed because sand is acidic. Non-metal oxides are usually acidic. You add limestone, which is calcium carbonate is basically chalk or marble. You add limestone to it. It decomposes to form a metal oxide, which is basic. Non-metal oxides are acidic and they react together to form a salt, which is called calcium silicate and also known as slag. Slag is low density and floats on the surface of the molten iron. And slag prevents oxidation of molten iron. Like the molten iron is covered or protected by slag. So it doesn't come in contact with oxygen in the air and doesn't really rust. So we did all of this in detail. We talked about the types of steel. There were high carbon, low carbon, stainless steel, and all of that. And now for very reactive metals, the only thing that's possible is you have to do electrolysis. That's the only possible thing that you have to do, because you can't reduce it with carbon. Only molten electrolysis. So if you want to form Na from NaCl, you would have to melt the NaCl. There's going to be molten NaCl. So there'll be sodium ions and Cl ions. In electrolysis, one terminal, it's sending electrons. That's your cathode. The metal is always attracted to the cathode because the cathode is negatively charged and the metal ions are positively charged. So they're always attracted to the negative cathode, and the metal ions go over there and they gain electrons from the battery and they form sodium metal. You'll find sodium metal on this side. Now in extraction of aluminium, you're going to do exactly the same thing. You'll do the electrolysis of Al2o3. Now the thing is that bauxite is the ore of aluminium. It's got aluminium oxide, plus it's got lots of impurities as well. The impurities are in the form of these other metal oxides. So it's not just aluminium oxide. Now the thing with aluminium oxide is, and that's step one, you've got to remove the impurities first. You have to get rid of the Fe2O3 and the other metal oxides. And the way you do that is Al2O3 is amphoteric, which means it can react with both acids and bases. Metal oxides are usually basic. So what you do is you dissolve the whole ore. I mean, the ore contains both things. It contains, so the ore contains both of these things. So it contains Al2O3 as well as Fe2O3. One of them is amphoteric, the other one is basic. When you dissolve it in NaOH, so Al2O3 dissolves because it's amphoteric. It can react with acids and bases both. Fe2O3 is basic. It's not going to dissolve in another base because base don't react with other bases. So Al2O3 dissolves in concentrated NaOH as it is amphoteric. Fe2O3 and other metal oxides don't dissolve as they're basic and they're later filtered off. So if they're not going to dissolve, the solid Fe2O3 will be filtered off. And that's how you get pure Al2o3. And that's how the other metal oxides are removed. So that's the first step, followed by the second step now. Is the previous step clear? Is this clear, yes or no?
Yes, sir.
Now, once you've got Al2o3 purified, the next step is you do electrolysis of that. So the next step is electrolysis of Al2o3, and that to molten Al2o3. So electrolysis is done. Remember, you just have to connect electrodes to a battery. So this is how the electrolysis is going to be performed. It's going to have these electrodes, which are going to be dipped into the electrolyte. So you'll have these lots of electrodes. So here's another one. And here are some more. So it's like the electrodes are comb-like structures, which are those are your electrodes that are dipped, and these electrodes are connected to a battery. So all of them are connected to a battery, and they're connected to the positive terminal of the battery. So that's one thing. And then your container is the cathode. Your container is lined by graphite. You can explain that. So your entire container has this lining. It's made out of a substance called graphite, and it's connected to the negative terminal of the battery. And this is what's going to happen. The negative terminal is the one that's going to try and send electrons. Battery is trying to send electrons constantly. There's going to be a constant stream of electrons that is going to be sent. So there's going to be current flowing, and this is what current is. Electrons are going to be flowing towards the container, and the positive terminal is the one that will be pulling the electrons back. So the electrons would be pulled back by the positive terminal. So you'll connect the two things to two terminals of the battery. One of them is positive, the other one is negative. This one is made, I mean, the anode is made out of graphite. So the substance, which is carbon is so graphite is carbon. Most of your battery terminals are made out of graphite. So graphite anode, which is basically carbon. And the container is going to be lined with graphite so that the container can conduct electricity as well. Graphite has free moving electrons. So if the battery starts pulling electrons, the electrons would start moving. So you need graphite. The container would be covered with graphite. So it's going to be lined with graphite, so that electrons can move around. And in this container, what you're going to add is now in this container, you're going to add your purified alumina, which is Al2o3. Now, and it will be in molten state. So that means Al plus 3 ions and O minus 2 ions will be roaming around. In molten state, they'll be able to freely move around. So I'm going to draw lots of Al plus 3 and O minus 2 ions all randomly moving around. So I'll have lots of Al plus 3 and O minus 2. So this is electrolysis of Al2o3, which we had purified in the previous step. So that's my alumina, Al2o3. Previously, remember, it was called bauxite because bauxite was a mixture of Al2o3 and impurities. So this is bauxite. We purified bauxite. We got pure aluminium oxide. The other metal oxides got removed. Now, what will happen now is the next step is that the positive terminal. Okay, just wait 1 second for the azan. So now the last step is this is what's going to happen. The oxygen minus 2 ions will all get attracted to the positive terminal, which is the top anode. So they're going to get attracted to all the positively charged anode because they're connected to the positive terminal. So anyways, they're connected to the positive terminal. So the O minus 2 ions will all be attracted to that. And the O minus 2 ions will start to lose electrons. The battery will start pulling electrons away from them. And the O minus 2 ions will, because the battery is pulling electrons. So at anode, this is what's going to happen, that O minus 2 ions. And remember, it's diatomic. O minus 2 ions will, there should be 2 O minus 2 ions. They'll lose a total of 4 electrons and they'll form oxygen gas molecules. Oxygen is diatomic, so you need two oxygen ions. 2 oxygen ions. So each oxygen ion would lose 2 electrons. To form O2, you need 2 oxygen ions. So in total, they will lose 4 electrons. And oxygen gas is going to be produced. What happens to the other ones? Al plus 3 will get attracted to the negative container. The container was connected to the negative terminal. The reason it was negative was because the battery was constantly sending electrons. So there are lots of electrons over here. And there are lots of electrons that are coming in, which is why the whole container would be negatively charged. The battery is constantly sending electrons. Now, when Al plus 3 goes over there, the Al plus 3 would have to gain electrons. And it would form aluminium. And aluminium metal is going to be produced. So the bottom is the one, the container is the one where aluminium metal is going to be produced. So I'm going to repeat what's happening. You had Al2o3, you had aluminium ions, and you had oxygen minus 2 ions. One of the terminal was positive, connected to the positive terminal. So all the negative ions, they got pulled or attracted to the positive terminal. And all the positive ions, they got pulled and got attracted to the negative terminal, which was connected to the container. And at the positive terminal, the battery is pulling electrons away from them. So oxygen ends up losing electrons. O minus 2 ends up losing electrons, and the O minus 2 ions, they turn into oxygen gas. The Al plus 3, on the other hand, the battery is sending electrons. So the Al plus 3 ends up gaining electrons. It ends up gaining electrons to form aluminium. So you'll have these two main reactions, one at anode, one at cathode. And that's how aluminium metal is going to be formed in the container. So aluminium metal is going to be formed in the container, and there would be secondary reactions that would be taking place at there'll be secondary reactions that will be taking place at anode. One is that the anode was made out of carbon. So another reaction that happens is that the carbon anode starts to burn. Because the oxygen that is produced reacts with the carbon that is graphite, and it ends up producing carbon dioxide or carbon monoxide. So you get a combustion reaction. And these anodes, because they're constantly burning away, because oxygen gas is being produced, and remember, they're made out of graphite, they're constantly burning away, which is why they need to be replaced. Because they burn up. Another thing about this is that you have to since you have to use molten conditions, because only in molten state are the ions freely moving around. So to keep this molten, the temperature that's used is 950 degrees centigrade. So I'm going to write that at the end. So 950 degrees centigrade temperature is used Why? Because you want Al2o3 has to be molten so that the ions can freely move around. Like if they want to get attracted to anode, or if they want to get attracted to cathode, they should be able to move around. And another substance that's added into this mixture is cryolite. Now, cryolite is a very important substance. The reason cryolite is added is that Cryolite is a substance called NaClF6. This substance is added so that the melting point could be decreased because aluminum oxide melts at a very high temperature. Like if you look at the melting point of aluminum oxide, that's really high. Around 22,000 degrees centigrade. So it's got a pretty high melting point. That requires a lot of energy. So industrially, it's not feasible to melt aluminum oxide because it's got a really high melting point. It's going to cost you a lot. So how do you make it molten? You make it molten by adding cryolite. Cryolite is a substance that decreases the melting point of aluminum oxide. It helps it dissolve. So that the ions can freely move around. So it decreases the melting point of and reduces economic cost. So that is the complete detail. They're going to ask you about Cryolite. Why do you add that? You add it because, and this is, we can also quote that without Cryolite, aluminum oxide melts at 2072 degrees centigrade. So that's a really high, melting point. So without Cryolite, aluminum oxide melts at a pretty high temperature. So which is why Cryolite is very important, because without that, the economic cost will not decrease. You've got Al2o3, it should be molten, that's one thing. And then you want, so that's it, that's all the details. So remember, I'm just going to go over the details once more. You need bauxite, which is the ore. Bauxite kind of looks like this. So that's the ore of aluminium. So it's a mixture of aluminum oxide and iron oxide. The reason it's red is because it's got iron oxide. That's like rust. So rust is reddish in color. So what you need is, you don't want iron oxide in it. You want aluminum oxide. You want to keep that. You don't want iron oxide. So you dissolve it in NaOH. And because Al2o3 is amphoteric, it will dissolve. The other one will not dissolve. And you simply filter it out. Then what you do is you do electrolysis. Once you've gotten pure Al2o3, you melt it and the ions move freely. The negative ions, oxygen ions, they get attracted to the positive anode, the positive terminal of the battery. And the positive ions, they get attracted to the negative terminal of the battery, which is the cathode. This one is the anode, this one is the cathode. Once that happens, the Al+3, the battery is sending electrons, so Al+3 ends up gaining electrons, turns into aluminium. The oxygen -2 ions, they end up losing electrons and turn into oxygen. And there's some other reactions that also happen. The oxygen starts burning up the anode, which are made out of graphite. So they need to be replaced. The carbon anode burns up and turns into carbon dioxide. So they're constantly catching fire because oxygen reacts with carbon. And the temperature is 950 because the Al2o3 has to be molten. And for that you need Cryolite as well, because Cryolite reduces melting point and makes it easy for the Al2o3 to melt. With Cryolite, I mean, this should be without Cryolite. Without Cryolite, the melting point would have been really high and the cost would have been pretty high as well. So which is why Cryolite is very, very important. Now, there's 3 properties of aluminium. One of which is, now we're going to talk about uses of aluminium. Now, aluminium used to be very useful. Previously, like we as humans, we were using steel a lot. Then we stopped using steel and we started using aluminium. We started making windows and doors out of aluminium. Previously, they were made out of iron. Then we stopped using aluminium, and now we have actually started using PVC, like the doors and windows and stuff, and the wooden floor. They're all made out of plastic now. So even aluminium is kind of old-fashioned now. But aluminium was a good replacement for iron. Iron used to rust a lot. So number one is, why is aluminium so good? Aluminium is good because it does not rust. It does not rust or corrode. So why does it not rust? We just did study this previously as well, that aluminium, it actually does rust. But what happens is that when it rusts, it gets a coating of a thin coating of Al2o3 on top of it. But that coating is really shiny, unlike rust. Like iron does the same thing, but iron has this reddish brown iron oxide layer on top of it, which is powdery. It's like it quickly corrodes. Al2o3 coating is tough. It's shiny. It's unreactive. I mean, it looks good as well. And it's non-porous as well. So nothing can actually pass through it. So the aluminium gets protection. It gets a layer on top of it, which kind of protects it. So the coating is tough, unreactive, and non-porous, and protects aluminium from further rust, from further corrosion. So you might have seen aluminium doors and windows, which we can just Google. So aluminium doors and windows very often used, TK, they were recently, but now they're actually, I mean, most of this stuff around you, previously they used to make steel windows, like the old fashioned, if you go to an old house, they used to have windows made out of steel. So they so maybe it's kind of the same thing. So so previously they used to make windows and doors out of steel, but that was kind of especially the old-fashioned windows like this. They were made out of steel, but they would rust a lot, and the way so you always had to paint them. For aluminium, you don't need to paint them because most aluminium windows are not painted actually, because it's already shiny and it's not going to rust or corrode. So which is why aluminium is good. But now everything is being replaced by PVC. PVC windows and doors. Even the floor tiles are being replaced by PVC. That's kind of like a plastic. So this is the new thing that's in now. This is replacing, I mean, this is lighter and it's tougher as well. And it doesn't corrode as well because it's plastic. Plastic doesn't react with water in the first place. I said, but anyways, aluminum is still in. And not that popular. PVC is now taking over. Does not rust or corrode. The second thing is it's light, it's low density. So it's really light. Aluminium windows, etc. Aluminium as a material is really light. And the third property is that the third one is that it's a very good conductor of electricity and heat. So that's the third one. It's a good conductor of heat and electricity. Why is it a good conductor? Because it's got lots of free moving electrons. It's got more delocalized electrons because aluminium loses 3 electrons. So in the metallic lattice, you've got more delocalized electrons. So what could be the uses for this? The first one, I mean, the use for the first one is does not rust or corrode. So what do you make out of them? You make aluminum cans, lots of cans, food containers, foils. Uh, so because it's not going to corrode or rust. It's like it's not going to react with the food as well. It's light and low density, so planes are made out of it. So most airplanes are made out of they're made out of aluminium, and also it does not rust, so you don't see airplanes rusting away. And the last one is they're very good conductors of heat and electricity. So most of your overhead high power transmission, most of the cables that you see around you, not in the house but outside, like high power transmission, they're actually aluminium. They're silverish in color, and those cables are made from aluminium. So these are the 3 main uses for aluminium which you have to remember. So is this all clear? Amna, is this clear? Zainab, is this clear? So let's continue next time. Okay, take care. Hafiz.